In this video, we're going to continue our discussion of significant digits. Whereas the last video we were focusing more on the measurement part of the process, today we're going to focus on significant digits in calculations and proper rounding techniques to make sure that our answers match the quality of the measurements we originally made. Let's go over some quick learning objectives. First thing you need to be able to do is be able to identify the number of significant digits in two places. Any type of number, and those numbers I think come in two categories. Numbers that you measured. Now significant digits are digits that come from measurements, so these actually end up being very easy. You know which digits were measured. When you look up numbers, however, you don't have that same kind of knowledge, and we need to have some rules. So looking on significant digits and numbers that you looked up is a little harder to do. Once we can identify the number of significant digits, the next step is to be able to correctly round the answer to a calculation based on the number of significant digits that were in the original measurements. As we'll discuss, the quality of information comes from measurements only, therefore the answers need to reflect that quality. So these are two things you guys need to be able to do. Before we start, let's do a quick recollection of what the stuff we talked about before with significant digits. A significant digit is any digit in a number that came directly from a measuring device. And we said that these were important because these digits carry meaning associated with them. They represent something real in the world, some object or some event that you recorded. Significant digit, if you recall, is also a measurement of the quality of your measuring device. More significant digits translates into a better, more high-quality measuring device itself. Now, the last thing I want you to remind yourself of is what we have here on the bottom of the screen, and that is that significant digits can only come from a measuring device itself. So this information that we were talking about up here, this information we have associated with a real object, only comes through the measuring process. That needs to be carried through, as we said a couple times now, into the answers that you actually calculate. So let's talk about that process a little bit. The scientific process starts in the lab itself, where you guys are going to be making your measurements. Those measurements then get recorded into your lab notebook as data. That data then probably requires some sort of mathematical calculation in order to process some sort of answer from the data. And then finally, that allows you to draw conclusions about your lab. That's the experiment we did. Now again, as I mentioned before, in this process, here is the only step where we actually get new and unique information, this research part. And that new or unique information has a quality associated depending on what type of measuring devices were used in the process. It makes sense, at least I like to think it does, that going through the process of data all the way through conclusion, the quality of those measurements really can't get changed. We can't expect to get better measurements somehow through the calculator. So our calculator can't improve the quality of the measurements we're making. The only thing we could do to improve the quality would be to go back to the lab and remeasure things using a better measuring device. As a result, and as I've said a couple times now, we need to make sure that when we do these calculations, that the quality that we had here, the quality of those measurements, gets reflected in the quality of the answer that we have over here. We certainly don't expect to get a really great answer from lousy data. And likewise, we wouldn't expect to get a lousy answer from really good data. There has to be a correlation. And that's really what this video is about, is making sure what we do here in the lab is linked over here to what we get in terms of our conclusions. So just as a summary of what we just talked about there, and this is something you can try to write down a little bit more clearly, is data cannot get better through calculations. The answers to any calculation, therefore, must be rounded. You got to get rid of all that extra significant digits, all that extra data that doesn't really correlate to something. You got to round that away so that eventually it matches the quality of the data from your original measurements. And again, the goal here is to make sure that the answer we get is true to the measurements we originally made. To do all this stuff, you've got to be able to handle these things down here in the bottom. We've got to be able to determine how many significant digits there are in any number. That's going to determine how much we have to round. And then we also have to use our rounding rules to figure out how to round our final answer appropriately. So this is what the next couple slides are going to be about, is tackling these two topics right here. So really quickly, before we move on, a couple of quick ideas here. If you measure the number itself, as we kind of mentioned, significant digits is super duper easy. Counting them is not a problem because you actually made the measurement. If you recorded off of your measuring device that the length of an object was 3.21 centimeters, you automatically know that the 3, the 2, and the 1 came off of your measuring device, and as a result of that we would say that this measurement has 3 significant digits. That's nice and easy. And any type of measurement you make, you're always going to have this information pretty much ready to go. If it's a given number, meaning this is something you did not record yourself, you don't know what digits were measured and what digits weren't. For example, I can give you the number 1,000 meters. Well, was it measured to exactly 1,000 meters down to the individual meter, or was it an approximation where 1,000 really could be anything between 501 meters all the way through 1,400 meters, we'll say, as a range. I think it's actually a little wider, but my point is it approximation or is it exact? Because you didn't actually measure this, you need to have rules in order to figure that thing out, and that is what we're going to talk about next. So we have 4 of these rules. Rule number 1 is that all non-zero digits are significant. When I say that, I mean in this number here, let's say the number 267, 2, 6, and 7 are all non-zero. Therefore, we would have 3 significant digits. The rationale behind this is that you cannot record a non-zero number. You cannot record a non-zero number other than 0 without changing the value of your measurement. And if you're changing the value of a measurement with non-zero digits that don't come from your measuring device, you're just making stuff up. And if you're making stuff up, clearly you're not really measuring anymore. So that's our first rule, and I think this is one of the easiest rules to pick on. The good news is that this covers 90% of the stuff you're going to be dealing with, and as you might guess, the rest of our rules, we have 4 in total, are going to deal with the other digit we haven't talked about yet, which is the digit 0. So that's rule number 1 tackled. Let's see if we can take a look at rule number 2. So as I said, rules number 2 through 4 deal with this digit 0 and when that does and does not count as a significant digit. So our rule 2, any final zeros, and the key term here is that final 0, any final 0 after the decimal place are considered significant. And the example I can give you is the number 1.00. Here we have 2 zeros. They're at the end of the number, final, and they are after the decimal place. These 2 zeros, according to this rule, count as significant digits. And likewise, the 1 counts because it's a non-zero. That's back from rule number 1. Here in this digit, we have 3 significant digits in this number. Now, the rationale behind this is the fact that these zeros serve no mathematical purpose. As far as your calculator is concerned, they're worthless. If they're not there for a mathematical purpose, they must be there. They are written to represent measured places. And what would happen in this particular scenario is you'd use your meter stick, you record the distance you were recording, and when you recorded that, instead of having your object land somewhere in the middle between your gradient lines, it actually landed directly on the gradient line, and as a result, you recorded 0. You want other researchers to know you actually made this recording, therefore you take the time to write the zeros in to show the quality of your actual measurement. All right, well, let's at this stage move on to our next rule. Rule number 3, again, deals with the digit 0. And this rule I like to call the sandwich rule. What it basically says is that any 0 that is sandwiched between 2 other significant digits are also considered significant. A good example of that would be the number 1001. Well, our first rule tells us that the 1 and the 1 are significant digits, and as a result of that, these 2 guys are sandwiched, making them significant digits as well. This number has 4 significant digits in it here. Again, the rationale, if you measured the ones place out here, or the thousands place, I'm sorry, and you measured the ones place over here, we've been forced to measure all the places in between. So you must measure the places between two other measured places. There's just no way we could have gotten this one data if we didn't already know the data from others. And it doesn't matter how many zeros are sandwiched. You could have a number stretch out as long as you want. As soon as you got that sandwich thing going on, everything in between would eventually follow that sandwich rule. All right, well, let's take a look at our last rule. Zeros acting solely as placeholders are not significant. And here's the first time we have zeros that don't count. If you're not comfortable with the idea of a placeholder, that's a key word here, placeholders. The purpose of a placeholder is to do exactly what it sounds like. We'll take a look at the number 100. We know from rule number 1 that the 1 in front counts, but these zeros here are doing something different than the zeros we've seen so far. These zeros here need to be present for our mathematics to work. If I remove them, it would no longer be the number 100, it would be the number 1, and that's a different value. Therefore, those zeros are there for math purposes, and they don't necessarily represent that a measurement was made. This number here only has one significant digit in there. The way you can check for these guys, sometimes students have a hard time identifying something as being a placeholder or not. The way you can check is that if you remove those zeros and the value of the number changes, then they are placeholders. And if they're placeholders, that means they are not significant. One way I like to indicate that, I put little X's through digits that are not considered significant digits. So there's our 4 rules. Depending on the scenario you're involved in, you're going to be using one or up to all 4 of them. And I think the next thing you need to try is a little bit of practice. It's not a difficult thing to do, but I think you need to see some problems in front of you before this is really going to start to take effect a little bit. Take these 5 answers here, or these 5 numbers here, and see if you can identify how many significant digits are in each, and also try to identify which of the rules that you use to make that determination. All right, really quickly, here are the answers to the problems that you guys just tried. We'll go through these really quickly. Question number 1 here has 5 significant digits. It's all 5 of them are non-zeros. This only uses the first rule, so that's a piece of cake. Taking a look at question number 2, we only have 2 significant digits. This one's a little trickier. These zeros are both acting as placeholders. These guys don't count. If I took them away, it wouldn't be the same number anymore, which means they're serving a mathematical purpose and they don't represent a measurement. Likewise, the same thing's going on here. These 2 guys are placeholder zeros, therefore we can ignore them. Go one step further, we go even further. All placeholders. If I take any of these zeros out, they change the value of the number. They serve only a mathematical purpose. Take it one step further, though, and add this 2 on the end. Now, all of a sudden, these 2 digits count, and everything in between counts via rule number 3, which is the sandwich rule. This guy has 8 significant digits, and that's a lot of significant digits. Now that we have a basic idea of how to determine the number of significant digits, we can now apply this information to actually doing calculations with significant digit stuff. So let's talk about those calculation and rounding rules. There's only one rule to worry about here when doing math with numbers with significant digits, and that is right here. The answer you have, whatever the calculation is, must be rounded to match the quality of the data originally collected. And we've actually said that a couple times right now throughout the video. It's got to match, and that's the key term. You're only going to round during the last step. I get this question all the time. I don't want you rounding every single time you do a step. If there's 5 steps and you round every time, you potentially are rounding yourself further and further away. We only round once, and that's at the very, very end. Now here's the other key tip here. We're going to use what I like to call the weakest link approach. When you're dealing with this rounding, you're going to have many data values that you're combining together in your calculation. Whichever one of them is the worst measurement, whichever one of them has the fewest significant digits or the fewest decimal places, that unfortunately is the one that is going to ultimately limit your answer, and that's the one you have to round your answer to match to. So you're going to round your answer to match. The rationale behind this is that the poorest measurement is going to introduce a lot of uncertainty into all of your calculations, and the other measurements won't be able to undo that uncertainty. If you don't know what's going on in the 10,000th place of a measurement, then you won't be able to add up what's going on in the 10,000th place, and as a result, that digit's going to be lost to you if that poor measurement exists. If you want to get that information back, you're going to have to redo that poor measurement and then have your data get some information in that 10,000th column so that you can do the addition you need to do. Again, I think this is a difficult thing to see in discussion. I think it's something that's a little clearer when you actually see it in action. Now we have two groups of rules here. We have rules for multiplication and division, and we have rules for addition and subtraction. The multiplication and division rules are relatively simple. You're going to round your answers so that they have the same number of significant digits as the poorest measurement that you made. And that's a key here. Notice I highlighted in yellow, the same number of significant digits. Let's talk about a quick example. We're going to start with the number 10.514, and we're going to multiply that by the number 2.3. You would put this in your calculator just like normal, multiply these two together, and you're going to get the answer of 24.1822. And that's the raw answer that your calculator spits out. Now your calculator spits all these decimal places as a kind of a byproduct of the structure of mathematics itself. That doesn't mean that these decimal places actually represent something real. They're just a product of math, and as you might have noticed, math is kind of blind. It just crunches the numbers. We go back over here and we look at the original data we started with. We have 2.3. This guy has two significant digits. Both of them are non-zeros. And then we have 10.514. This guy has 5 significant digits. The 514 and the 1 here all count, and then this 0 ends up being sandwiched. Now, this is a great measurement. This is not so great of a measurement, and as a result of this poor measurement, we can't combine these terms with these terms out here, and the end result is a lot of this information gets lost. Therefore, we have to round our answer to match, and in this case, we have to round our answer so that it has 2 significant digits. When you round stuff away, the number you're eventually going to end up with is the number 24. Now, you might say to yourself, why would I round to 24 when I knew all this information? But my answer to that would be is you didn't know this information. This is your calculator's guess as to what these numbers would be, but in actuality, since no measurement was made out here, the end result is we have to limit our answer to what we know is true. We know 24 is an accurate combination of these two numbers. We don't know if the 1, the 8, the 2, and the 2 are. Therefore, we have to limit those out. It can be frustrating at times, but these are the rules, and it keeps you honest with the math that you're doing and makes sure that, again, the answer reflects the quality of what was originally done. So, that's multiplication and division. We round to match significant digits. In addition and subtraction, things are a little bit different. In this scenario, we round so that we match the same number of decimal places as the poorest measurement. So again, we can do an example here. We'll take the number 114.3, and we will add that to the number 17.1482. Put that into your calculator and you'll get a numerical answer of 131.4482 as our numerical answer. And this is just your calculator doing its raw numbers here. Again, we go back and check. We have 1 decimal place here in this number. We have 4 decimal places here in this number. This here is a great measurement. It's got a lot of significant digits associated with it. This one, less so. Unfortunately, it's this guy that limits. So we have to make sure we round our answer to match the number of decimal places, not the number of sig digs this time. We got to round this guy so that it rounds out to 1 decimal place, and I actually believe that's going to end up being 131.5 as the answer we're looking for here. You got to be a little careful with this. This 8 is going to cause this guy to round up to a 5, and this 5 is going to cause this guy to round up to a 5, and that's how we get the number here. So again, despite the fact that our calculator spit all this information out, the only decimal place we're confident about is the 5 here. The 4, the 8, and the 2 represent mathematical byproducts, but we don't have the data in the original measurements to back those digits up. So we're going to limit to what we actually do know, and that's the 131.5. All right, now that we got our 2 rules pinned down and ready to go, here's another round of practice problems. Again, you're supposed to plug these into your calculator first, get a raw answer, and then determine significant digits in each case and round your answer to match. So pause the video, take a few minutes, and see if you can't get some answers for these. And here we have the answers to our problems. We'll go through these one at a time so we get a good idea of how this whole process works. Taking a look at our first one here, this is a multiplication problem, therefore we have to worry about how many significant digits we're dealing with in each case. These are all non-zeros. Rule number 1 tells us we have 3 sig digs here, and rule number 1 and 3, I believe, tells us we have 4 significant digits here. These zeros are sandwiched, therefore they count. We do the actual math on the calculator, and we get the number 713.713. But we got to round to match our poorest number, which means we got to round to 3 significant digits, ending up with the overall answer of just 713. Again, this might be a little frustrating, but this is the limit that we can use in terms of our calculations. These other digits here are just a product of the mathematics. They don't necessarily reflect an actual measurement anymore. We can do the same operation, but in this case we'll do it with addition, and the rules change a little bit. Now we're not worried about how many significant digits we have, but how many decimal places. We got 3 decimal places on this guy and no decimal places on this guy. So when we add the two of these together, we get 1001.713, and we got to round it down to having no decimal places. We actually should be getting 1002 here, right? Just like up here, we should be getting 714. The 7 rounds into the 3, the 7 here rounds into the 2. Either case, the result is pretty similar though. The goal here is that we have no decimal places to match the no decimal places we had right there. Moving along, here we got division again, follows the same rules multiplication. You got to count significant digits. We have lots of them here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 sig digs in this number. But this number over here actually only has 2. The 4 and the 8 count. But these guys are placeholder zeros. If I remove them, the value of the number changes. Therefore, we only have 2 sig digs here. And even though we get all this information out of our calculator, the only usable part of that information is the 190 here. That's the only digits we're confident about that we know are true. The rest of these digits, we don't have enough data from our original measurements because of this poor measurement over here to justify writing these numbers down. Moving on, another subtraction problem here. Same rules as the addition. We're going to have to count decimal places this time. We got 1, 2, 3, 4 on this guy, and 1, 2, 3, 4, 5 on this guy, which means our answer has to be rounded to match the least, which in this case is 4 decimal places. We get 65.4555 when that 5 rounds up to 4. We can do another subtraction problem here, and I'm trying to illustrate the difference between multiplication and division and addition and subtraction. Same mathematics, same numerical answer, but this number has tons more significant digits. This is a ridiculously accurate measurement. Unfortunately, though, in addition and subtraction, that does not do us much good. We're still limited by the fact over here that we've got 4 decimal places, which means our answer is still going to have 4 decimal places. We get the same result as we got from the previous problem. As always, if any of this is still confusing to you, there's a lot of resources available online for you to check, and likewise you can come and talk to me after school and I'll be glad to give you a helping hand. Again, I said this in the beginning and I'll wrap it up here at the end. This topic shows up in every experiment, it shows up on every single test, and if it's something you're struggling with now, it's something you'll be struggling with then as well, and it'll haunt you for the rest of the year. Get it fixed today, that way you don't have to worry about it then.